So let me first explain the MSI protocol. The content has been taken from all of this. You could refer to all of this, but mainly the diagrams have been taken from these two references and also from Wiki. You could also refer to Hennessy Patterson, but then the diagrams shown there are much more complex to understand. Therefore, I've not taken the content from there. So the MSI protocol, like I said, is an invalidation-based protocol, and the key idea of all these protocols is to track the state of any of these shared data blocks. Now the MSI protocol is containing three states. It's like an FSM which contains three states for a cache block. A cache block can be in any of these three states. Firstly, it could be in modified state, which means that the block of the cache has been modified. That means it has been written to by the core. And this also means that the data is not consistent with the memory. That's because we are assuming, let's say, a write back cache. And this is very similar to having valid equals 1 and dirty bit equals 1. This means that we need to write back to the main memory before we evict this block. Then the cache block can be in a shared state, which means that this block is in one or more cache. So it is either in just one cache. That means, let's say we have P1, P2, and P3. So it could be just in P1's cache, or in P2's cache, or P3's cache, or it could be in more than one cache as well. But the data in the memory is up to date, which means that dirty bit equals 0. So this typically happens for reads, and that is when you call it as a shared state. Then the cache can be in invalid state, which means that the block is not present in the cache or it has been invalidated using the invalidation protocol. This is nothing but valid equals 0. Now the protocol also describes a few signals that get issued by the processor. So the processor could issue a PR read, which is it wants to read a cache block, or it could issue a PR write. That means it wants to request to write to a cache block. There are also a few cache requests, and these are the signals bus read X, bus upgrade, and flush. But going through it right now may not make sense. So I'll first describe the protocol, and while describing it, we will go through these signals. So this is the beginning of this protocol. So I'm assuming there are three processors, P1, P2, P3, each of them having a cache, a local cache, and the data in these caches can be shared between each other. And this is the common shared bus, and we have the main memory here. I'm only going to indicate the M, S, or I status of these blocks along with the address or the data. I'm not indicating the tag, valid, or dirty bits. Now the FSM on the right top corner that you're seeing here is for the current core which is sending the request. So for example, if processor 1 is sending a read request, this diagram should be referred to, the top right corner diagram. And if some other processor is trying to read or access the bus, then you have to refer to the bottom right corner. So I'll explain this as we go along. Now let's say the processor 1 tries to do a read on a certain address location A. Initially the cache is empty, so the data block is invalid. So we are in the I state here, and we issue a PR read. The processor issues a PR read. Now because the data is not present in the cache controller will issue a bus read signal on this bus, which will go to the main memory. Now that is this bus read that you see here. So when a read miss occurs in a processor's cache, it sends a bus read on the bus, and it is expecting the data from the memory. So that is this bus read signal. So the processor read resulted in a cache miss. It issues a bus read. Then main memory sends the data back. So it sends the data back, and the data has now been put in the cache. Now the state of this cache block, which was earlier invalid, has now changed to shared. Now, why did it change to shared? If you refer to the diagram here on the top right, if you are in the I state and you get a processor read signal or a bus read, then you got to change to shared state. This means that the, by our definition, of the shared state, this means that the block is in one or more cache and the memory copy is up to date. And therefore, we are currently in the shared state. And we have not yet accessed the data from the other cores. Therefore, we don't need to look at this particular FSM. Now, next, let us say that processor 1 tries to write to this same cache block. And we assume that we have a write back cache. Now we have a cache hit. Now this is a PR write issued by the processor 1 in the shared state. Now again, what should be the next state of this uh, core? You should refer to this FSM. First, let us just go by our understanding. Now currently, if it is in the shared state, which means that the memory copy is up to date. Now processor 1 is trying to write to this cache. Now we are assuming a write back cache, and therefore the memory copy is not going to be up to date. I'm going to write a equals 2 to this data block. By our definition of these states here, if I'm going to write to a cache block, then and if the data is inconsistent with the memory, then I got to change to the modified state. So I'm going to now change this state, shared state, to modified state. So if you look at this FSM on the top right, that's what it says. If currently it's in the shared state and you get a bus, if you get a processor write, PR write signal, you got to change to the M state. Now we have not yet come to this second diagram here. We'll do that eventually. We will also currently assume that all the other cores have the cache block in the invalid state, which means either they do not have the cache block or they already have it in the invalid state. Now let us say that this is the latest status of the data in P1, a equals 2, and it is in the modified state, which means it is inconsistent with the main memory. And now the processor 2 issues a processor read for this data. Now, looking at this FSM, if it is in the I state and it gets a processor read, I need to change to S state. But before that, we should also check what is happening on the other cores. Now, processor read. Now you should also understand what are these two signals here. Now, if the block is in the I state, like it is in processor 2, and you issue a processor read request, then along with it, a bus read is actually sent. That is what this means. I should have explained it in the first slide. So if a processor read request is sent by the processor, and that means that the data is, let's say, a miss in the cache, then it sends a bus read signal on the bus. So the bus read has now come on the bus for the same cache line. Now what will the other processor now do? The processor P1 has this block already and it is in the M state. So just going by our rational thinking, if you just think logically, what should now happen is that processor 1 should send this latest data to processor 2. That is because the memory does not have the latest data. So just by our logic, we should know that a equals 2 should be sent from P1 to P2. Now that happens through the change of these states. Now look at this diagram on the bottom right corner. Now this diagram should be used by the other processors which are looking at this bus read. Now this processor P1 is currently in the M state. So currently it's in the M state and it sees a bus read on the bus. So now what should happen is it should send this signal called flush on the bus. So it sends a signal called flush on the bus. So what this flush means is that it is going to write back uh, this data from before it changes to S state. So the flush here is not the same as removing the data. There could have been a better terminology for this, but that's what it is. So so the moment this P1, which is in the M state, sees a bus read, it sends a flush signal on the bus. So what this does is it's going to write back this data to the memory, and the cache controller is going to check these other caches. So this cache controller, the P1's cache controller is going to send this data A equals to this processor 2's cache controller. So basically, there are two activities happening here. One is data is being written back to the memory, and the data is being sent to P2. And all of this is happening through the cache controller of both the cores. So now, why are we actually writing back this data to the main memory? That is because once we share this data between the two cores, we already know that the first core has to change its state from I to S, because on a read, you're going to change from I to S. Similarly, this data, which was earlier in the M state, this is M state, and it sees a bus read, so it is also going to change to the shared state. So now both the cores are going to be in the shared state. And by the definition of shared state, S means valid equals 1 and dirty bit equals 0, which means that the memory should have the same updated value. So that is why we first write the data back, indicating it through this flush signal, and then we also send this data to the processor 2. So basically, there is no direct memory read by processor 2, but it is communicated through the two cores. So this is how you use these two diagrams. So let us go through one more example. So here, let me just complete the same case and before we go to the next one. So here, basically, this is the same slide as what we saw earlier. This is the same slide as the previous one. So this is what is called as a cache to cache transfer. So there are two ways in which you could do this. Uh, One is you could ask core 2 to keep uh, retrying it. So in the meantime, core 1 can write the data back to the memory, and then the core 2 can read from the memory. So that is one option, but that's going to have a larger memory latency. But the other option is what we just showed in the previous slide. The core 1 informs the memory that core 1 will respond to this read request. Core 1 will send the data to the core 2, and both of them change the state to shared state. So this is a much better way of implementing it.